But anyways, oh, it's being recorded. Okay. Well, anyways, the story starts off by Marcel Deprez. He was, I believe, like a French engineering student. No, no, no. He was working at the French university. Um, yeah, he was working at one of the French universities to work on, yeah, just generally transmission of electricity through power lines. And this is during like the 1880s, 1890s, that kind of time period. So this is like very early on, and this is like him just trying to build up like a proper working system. And he actually did. He made the first like properly recognized power line in 1882, and this was showed off at the International Exposition of Electricity, the first ever international exposition of electricity. And what's really cool about this event here is that at the same event that he was showing off the world's first power line, um, the standards for the ohm, the volt, and the ampere were like standardized for all of history. Now, obviously, they've like I guess been more accurate since, like there's slightly changes, but the general units were initialized during this time period here. And so the power line he created, I don't have a photo of it. I don't know if there's any photos out there, but it was 57 kilometers long and carried 2,500 kilowatts of electricity. So at the time, it was impressive, but nowadays, like 2,500 actually is quite little. But yeah, um, so yeah, that was kind of cool. But then this guy named Rene Thury came along, and he basically took the idea of using DC power for transmitting electricity to like a whole other level there. So this guy, he started off, or he was born in Switzerland, but then he went to France to work in a machinist shop of some kind. I'm not exactly sure how they work, but apparently, like back in the early 1900s, people would like just hire people in machine shops to make stuff for them. Um, and so, yeah, he would just make a bunch of stuff for other people. For example, he helped make the Graham machine, which is a kind of dynamo. Not exactly sure why they made this, but basically, what this device does is that it turns you turning the handle into electricity. So I guess it was like used for showing experiments with electricity or something. Not entirely sure, but yeah, he helped make this. Um, he also made this. This was one of the first steam cars ever made, uh, and he made it with his friend John Jacques. I don't want to say that. Never mind. But yeah, they worked on it together, um, and yeah, that was kind of it. Although, well, John didn't actually really work on it. He more financed it because he was a doctor, I believe. Yeah, they're just kind of friends, and they just make it because it's like fun. So yeah, it was kind of cool. But anyways, around the 1880s, he goes um, to the United States to talk to Thomas Edison because Thomas Edison also has like a bunch of projects that he needs to be made and stuff. And so he was just like talking with Rene Thury's machine shop to like see if they could like work on some kind of project together. Ultimately, they couldn't really work on anything together because they like didn't have much overlapping. But yeah, Thomas Edison and Rene Thury began talking, and Thomas Edison showed Rene Thury his design for a electric generator for producing DC power. Yeah, and at the time it was like kind of an all right DC generator, and so Rene Thury is like, you know what, I can make one better, and so he kind of did. He basically took Thomas Edison's design and just put six phases on it versus just the two phases from Thomas Edison's. And yeah, it worked a lot better. It produced a lot more voltage and stuff like that. And so yeah, later on, like a bit later, he began making like power systems, and he really was the biggest player when it came to DC power systems for essentially all the time that there were DC like transmission lines going around during the 1900s. So the way that his system worked is basically you just have the electricity go in series, right? And so, or yeah, you have them. Yeah, you have all the power sources be in series, and so that way the voltage going across is like super high. And then when it reaches the other side, you have all the components on the other side be in series too. And so therefore the voltage across each component is less than what you're having across the power lines because yeah, just as a general rule, right, you want to have your voltage high and your current low to transmit a lot of power long distance. And so yeah, for the time, Renee's theory was really like ahead of everybody else in the DC power transmission game. This was his longest ever power line, I believe, and it ran 200 kilometers and carried 30 megawatts of power at 150,000 volts. And you know, this is back in 1906, like over 100 years ago he did this. So that's kind of crazy to kind of think about. But anyways, as you guys probably know, Thomas Edison, the whole AC game kind of came around. And really like the biggest reason that kind of took off was because of the transformer, because you're now able to really easily turn up the voltage and turn down the voltage to make it so that transmission would be really efficient, and then use in the houses would be really easy because you didn't need to like rely on that extremely dangerous high voltage. And so DC, they try to keep up with this by trying to come up with ways to convert the DC power into AC and then turn that AC back into DC. So that way they could take advantage of like a transformer in boosting up the voltage to like send across wires and stuff. But ultimately, like these things were just not very good because when you have, well, so this is like a mechanical converter. And when you have like a mechanical converter like this, it just loses a lot of energy to heat and stuff. And overall, you just waste a lot of energy, and it's like, you know, you're wasting a bunch of money that way. So for the next 30, 40, how long ago was it? It was like, yeah, 30 years. There was like no real innovation coming along with DC power until this guy named Peter Kuber-Hurwitz came along. And he invented something called the mercury vapor bulb, which I believe is still kind of used today. Basically, it just uses mercury and it like sends a bunch of electricity through it, and it makes it so that the electricity or the mercury lights up because of the electricity. So yeah, this guy was like very into playing with gases and having electricity go through them. And so, you know, after tinkering around a bit, he also created a mercury arc valve. And basically what this did was it was able to turn AC into DC really efficiently. And that was like a really big innovation, right? Because now you can have something that can take the DC, or yeah, now you can take the AC that's like able to change and become like high voltage, and you're able to send it across power lines and stuff using DC. So that was pretty cool. And then, oh yeah, wait, no, this was 1902. Yeah, nobody really touched this technology until this guy came along, Uno Lamb, who is considered the father of high voltage direct current. So what Uno Lamb did was that, yeah, he was basically in charge of the mercury arc valve project in the 1930s. This project basically was all about trying to optimize that mercury arc valve design that was created back then and try to use it in a way that could actually properly convert AC into DC. And so, yeah, they worked for a fair bit of time, and then they actually were able to like scale up and create proper systems to convert large amounts of power into DC. And this is all through this company called AC. A is that how you pronounce it? AC? Yeah, that's a bit ironic. Anyways, yeah, I'll mention that guy, the company later. But anyways, uh, before I want to kind of go further, the reason why AC or DC is like more valuable than AC is because across long distances, DC power transmission is more efficient. Um, this is simply due to like how having the current go back and forth in the power lines um, has problems. It was something about like how the towers for like the power lines, so it kind of act as like mini capacitors in a sense, or they would have like some capacitance, and that would dampen like the actual flow going back and forth through the power lines. I'm not entirely sure, but I just know like the general rule is DC is more efficient if you have the same voltage and current. Obviously, getting to that voltage and current is like the big problem that everybody was struggling with. Um, this is wrong. I learned later this is wrong. Both AC and DC have corona discharge. Um, but yeah, there's such thing as corona discharge. If you guys didn't know what that was, basically it's kind of like a precursor to, um, I guess like electric arcs. Is that how you say it? I don't know, but basically what happens with corona discharge is that um, at those points where there's lights coming off, small amounts of the electrons are leaving the metal and they're flying through the air. And because they're doing that, it lights up everything. But yeah, another benefit of DC is that it just takes up far less space for the amount of electricity you can carry across. And this has to do with um, a lot of very complicated factors. um, let's see, what was it? It was basically when you have current like constantly going back and forth, what happens is that on like the actual wires themselves, the charge tends to like build up closer to the sides rather than in the center. Um, and so your actual usable area on everywhere is much less for a AC wire than it is for a DC wire, because with DC wire, since you're not having constant flow of electricity back and forth, you're able to optimize the entire area of the wire to carry electricity. Um, but a really cool thing with DC that you can't do with AC is that you can run it underwater, and that's exactly what Uno Lam, or not Uno Lam, uh, yeah, Uno Lam. Yeah, that's exactly what Uno Lam's team was really setting out to do with the whole Mercury arc valve project, is that they want to run wires underwater to power a small island that was off the coast of Sweden. And the reason why you can't do this with AC is kind of why there's a lack of efficiency for AC in long distances. And that basically, whenever, I don't know how to, I don't exactly know the specifics of it. Basically, whenever you have like an AC wire next to other things, the other things have like a capacitance to them, and it dampens the flow of AC for like however long it's being in contact with it. And so if you're running a wire underwater, you're going to have a lot of water that's around that wire. And that's going to act as like a gigantic capacitance, which is going to really decrease your efficiency for the amount of length that you're running underwater. But with DC, you don't have that problem at all. And so you're able to just run it into these places just fine. And so, yeah, that's kind of them just laying across the whole wire there. Um, this is kind of wrong, but this is also kind of to illustrate a point where like with DC, you can run like just a single solid core of copper to run the whole electricity through. And then with AC, you need 3 wires to do that kind of the same job. Uh, Also, with the fact that you can't really run it underwater. So, yeah. But yeah, so the Mercury arc valve project worked. They were able to convert AC to DC. And so the whole wave of like using DC power kind of blew up after that point. In the United States, we created our first DC power line in 1970. This is, I think, the longest one still in the United States. It runs from the border between Oregon and Washington all the way down to California. Carries well, it used to carry 1440 megawatts of electricity and ran that distance. But I'll explain that later. And this is what it looks like. That much electricity is carried through just that small of a tower. And so you imagine like if you have like an AC system, you'd imagine, or you'd have to like picture, I guess like 5 times that size in terms of just towers carrying electricity. So yeah, another advantage for DC right there. So yeah, Uno Lam, very influential, and he won a crap ton of awards. One thing that I was really happy with, or that was like really funny when I found it. He also won something called a Lam Award, and this is an award from named after a different person named Lam. Yeah, so it's called the Lam Medal, and it's for people recognized the to recognize outstanding design engineers in the power field. So, yeah. And this is also kind of another high voltage DC power system that got set up. I don't want to pronounce that. This was set up in the United States around World War II. The reason why they carried DC is actually really interesting. Basically, this power plant was set up like in the 1900s, and when the US went into the World War, they had a lack of electricity to power all of their power plants, and so they needed more. And so they tried to wire the system up, but the problem is that like the United States runs on 60 hertz electricity. This power plant could only produce 40 hertz electricity. And so to turn it into 60 hertz, they had to convert it to DC and then back into AC. And so they figured it'd be easier just to convert it into DC and carry it across and then turn to AC when they got to the place. So yeah, that was kind of cool. And this was set up by, I want to say General Electricity did this project, but I feel like I didn't research this enough to do it. Anyways, doesn't matter. But also during like the time that AC was, or ASEA was making their high voltage DC power systems, I think it was Russia, right? I think it was Russia. Moscow, is that Russia? Okay.
It is, yeah.
Okay, I'm not going to say it. Okay, yeah, Russia was like, oh yeah, we also want to like show off our DC might, and so they built up a couple power plants as well to like kind of show off how good they were with creating high voltage DC power lines. But they were okay. Like this was Uno Lam's power line back in 1906, and that carries 30 megawatts of power, 200 kilometers, versus 30 megawatts of power, 155 or 25. So I don't know. This kind of shows like how how good Rene theory was for his time period. But yeah, and then this was kind of another power line that they had. Um, this was the biggest in Russia at the time. Um, After this period of like the 1970s or so, uh, Russia kind of just completely stopped making high voltage DC power line, and so all of it kind of just went to AC to make them all and stuff. Um, and so around the 1970s, another invention that came out was the thyristor valves, which are kind of just transistors, but more complicated. I don't really understand how these work exactly. I know it's like they kind of open up when they have electricity into them, and then they kind of stay that way or something like that. Um, it's just more layered transistors, I think, is the general summary. But using these transistors, people were able to convert a lot more power much more efficiently versus the mercury arc valves that were used beforehand. And so, oh yeah, and so the name thyristor is kind of interesting. Basically, General Electric, they had their own kind of mercury arc valves that they're working on with some other gas called theratrons. I think theratron. But yeah, that was their like kind of gas valves that they were working on, and so they combined that name with the transistor, and they came up with the name thyristor. So I don't know, kind of a weird history there. But anyways, because of that thyristor, they were able to take those existing infrastructures of DC power lines, and they were basically able to boost them. So right here, it's able to carry 1,440 megawatts of electricity. And with the thyristors, it was boosted to 2,000 megawatts of electricity. So yeah, pretty cool efficiency boost there. Um, and
Wait, sorry. What
so
was the time difference in years?
uh, 20 or 14 years.
Nice. Wow. Okay. Sorry, carry on.
Yeah. Um, yeah, and so nowadays, these are really the two main players when it comes to the high voltage electricity game, Siemens and ABB. Now, what's really cool is that ABB is actually just the ASEA company from before. They, I think, got bought out by some bigger organized. No, it was some history. I'm not really too familiar with it. Oh wait, no, I have it in my notes. The company took groups from they merged with a bunch of other companies to create ABB because they didn't have enough capital to like enter like the world market beforehand. And so yeah, now ABB is kind of the largest player when it comes to the high voltage direct current space. So this is kind of a cool country. What country has the longest high voltage DC power line? Do you guys want to take a guess?
I almost want to say Russia.
Okay.
Well, you said Russia got discontinued, so probably isn't Russia after all.
Yeah, you might be right.
My guess is the U.S. Western half through the I forgot. I think there's some DC lines around there, but I don't actually know how long they are.
Yeah. So with the United States, that DC line that I just showed you from the Oregon to California, that's actually the longest we have in all the United States. The rest of them are shorter than that. But the country that has the longest power line actually has the three longest power lines, not just the longest. It's Brazil, believe it or not. That's because they have a lot of hydropower that they have along like I guess the northern part of their country, and then they have like a bunch of people living in the southern part. And because of those mountains, they have like a bunch of, or no, not mountains. They have a bunch of rivers there. Well, anyways, because of those rivers, they have a bunch of hydropower, and they need some way to carry that hydropower across.
Interesting. And so those are all those are all
High- DC.
interesting. So they're using
Yeah.
DC generators. Is that the thing, or are
I
they
don't know how they're
AC
producing
generators?
it.
And then they're like, well, we want to use DC. So
I'm guessing they're converting it to. I'm not sure how they do it exactly.
oh, that's cool
but
though. Okay.
yeah. And so yeah, in 2012, actually, 70% of Brazil's power came from hydroelectricity, and they're able to like really maximize it with grids like this. And China is actually working on a DC power grid, not just a bunch of DC power lines. I think they've actually finished making a grid last time I checked. But yeah, I guess their entire goal there is to just like connect all the highs and lows of all those DC power lines together to make it more like synced up or something like that. So yeah. And in terms of the UK, they actually have a bunch of DC power lines going across to all the different countries because a lot of places, right, they're separated by bodies of water. And so if they want to like sell electricity to one another, they can't send it through AC power lines because you can't really do that through water. And so they're all connected up with DC power lines that are going through the different bodies of water and stuff. Also, it makes it easier because you don't have to sync up the frequency of the electricity and stuff. So, yeah.
What do the different colors and textures of the lines signify? Do you know?
That was oh shoot, that was the current ones, ones that are being built, and then projected ones in the future.
Crazy.
I
Okay,
think
cool.
This was a little dated, but yeah. That's it.
Awesome. That's really interesting. So could we go over again? So what was the major benefit of having the DC lines versus having the AC grid? Like China's building the
They're
DC
building
grid.
out. Yeah.
Yeah.
They have an AC grid too.
Right,
It's
exactly. Yeah.
So the main benefit is just over long distances, you're gonna have more power loss with AC versus DC.
Really? Okay.
Yeah.
I always thought it was the other way around, and that's why we ended up using AC on all the
So
things.
we use AC because it's easier to convert it into high voltage, low current.
Oh.
Because all you need is a transformer to do that.
Sure. Oh, okay. I think I may be thinking about just why America is using 110 versus 240, and I think the answer to that is no reason except that we want it to be different. And so 110 is way more lossy than 240. I think that's what I was comparing to, but that's cool that DC would actually be more efficient.
Yeah.
I guess it's over. Yeah, I guess it's over long distances. I guess maybe that's the main key, at least for me. Yeah, because just like you, Tim, I always thought it was AC was a lot better, but I guess over long distances it kind of makes sense because most AC currents, at least that I know, are either sine or kind of square wave. So
right.
over long distances it loses some of its amplitude and it has So maybe now that makes a lot more sense.
Plus, like reflections based on resistance. I don't know. There was something in transmission line theory where it was getting crazy over long distances, where you actually have capacitance between the two, which I don't know how that looks with AC. DC.
We should probably stop recording here.
Okay, I can do that.
Yeah. So if I remember, whoops.